What is log base 3 of 81? All right, well, log base 3 of 81, I'm going to write out like this. Log base 3 of 81 equals x. Now, if I give you something in the form of log base b of y equals x, I can write that out as b to the x equals y. This is me transforming a logarithmic equation into an exponential equation. You would be my b, you would be my y, you would be my x, which means I can rewrite this guy as 3 to the x equals 81. Now what does that do for me? I can rewrite 81 as 3 to the 4th power. So 3 to the x equals 3 to the 4 means since they have the same base and they equal each other, I can say that x equals 4. Which means log base 3 of 81 is just 4. And that's it, we're done. Solve for x, we've got log base 2 of x minus log base 2 of 8 equals 3. Using our rules for logarithms, if we subtract two logs of the same base, that means we divide the insides in order. So this becomes log base 2 of x over 8 equals 3. Now, this is what I'm going to do. Whenever I'm trying to solve an equation and I notice a log there, I can get rid of the log by taking 2 to the of both sides. Whatever the base is, I turn these guys into exponents and I use that base as a new base for an entire power. Now, 2 to the log base 2 of stuff allows the 2 and the log base 2 to cancel out, and I could just drop down whatever's left in that parentheses. That's going to equal 2 to the 3rd power, which is 8. Now it's just a matter of me solving for x by multiplying both sides by 8, and 8 times 8 is 64. So my answer is B. The function g of x is defined by g of x equals log base 5 of log base 4 of x. Which of the following is an expression for the inverse? Now let's deal with that in a minute. First off, I have to handle this monstrosity. So I'm going to call g of x y since I'm going to end up dealing with the inverse anyway. And I have log base 5 of log base 4 of x, close it, close it. Now I need to get rid of both of these logs. The way that I can get rid of a log is I notice the base and pretend both of these guys are exponents and take that base to these powers. What that allows me to do is 5, log base 5, cancels out. On the left I have 5 to the y, and on the right these are gone and I drop down log base 4 of x. And you might be thinking, well, hold on. We have log base 4. Can I just do the same exact thing? Yup. If I have log base 4 in the way, by pretending you're an exponent, I could take 4 to the log base 4 and that'll cross out. Now I have to do the same thing over here. So now on the left I have 4 to the 5th to the y equals, well, just x. Now this is g of x. This is g of x. They want me to find the inverse. And in order to find the inverse, your first step is going to be swap the x and the y. So 4 to the 5 to the x is going to equal y. So the inverse of g is 4 to the 5 to the x, which is b. Very strange problem, but I like it. The function f is given by f of x equals 3 log base 4 of x. Which of the following describes f? They want to talk about whether it's increasing and whether it's increasing or decreasing at an increasing rate. So we're talking about concavity. We're talking about whether it's going up and to the right or down and to the right. So a log, traditionally, whether it's log base 4, log base 10, log base e, a log is going to look like this. By multiplying it by 3, all I'm doing is making it taller. So all I'm doing would be making it look like that. So it's the same type of behavior. So what it appears that it looks like is it appears that it's going up and to the right and it's concave down. Now that would mean increasing function. So f is an increasing function, f is an increasing function, f is a decreasing function, nope, f is a decreasing function, nope. Now if it's concave down, that means it increases at a decreasing rate. Concave down means the slope is decreasing, so it's increasing at a decreasing rate, which would get rid of u and leave me with b as my only option. So that's what you get for this one. A logarithmic function f is defined by f of x equals negative ln of x plus 4 on the domain between 0 and 5. Which of the following is true about f? Well, let's take a look at regular old ln. Regular old ln is logarithmic, which looks like this. Now, with this particular function, I'm doing two things. By multiplying it by a negative, by multiplying the ln by a negative, I am reflecting it over the x-axis. Okay, so I'm reflecting it over the x-axis. So let me do that. Let me draw a brand new guy. So now you are going to be spun upside down. Like that. Now the other thing that's going to happen is we add 4. That's a vertical translation, means we move up 4. So if we move up 4, this guy is going to be just like this. Okay? So I'm trying to get the arrowhead there. There we go. So it's going to look like that, give or take. So what do we have here? Well, we're not done yet. My domain is going to be between 0 and 5, which means we start here. Now here's the thing. I'm not allowed to take the ln of 0. That doesn't exist. Also, I'm not allowed to take the ln of a negative. So this is basically going to be a vertical asymptote for ln. The y-axis is going to be a vertical asymptote. So I can't plug in 0. And this guy is going to go up there forever for infinity. So the questions that are being asked is about its maximum or minimum values. This guy does not have a maximum value because it'll keep going up forever. So there's going to be no max. Now, if I cap this off at 5, it's going to bottom out right here, or wherever that's going to look like on the problem. I don't know how accurate this picture is. I just moved it up 4. But it's going to bottom out somewhere. So it will have a min. So it's not going to have a max, and it will have a min. And if that's the case, it's not going to have both. It will have a maximum. Nope. It will have a minimum, but no maximum. Yep, my answer is C. And D says neither. That's not the case. So I will have a minimum because of the fact that it stops at 5, and it won't have a maximum because this will keep going up forever right before it hits 0. The function f is given by f of x equals log base 3 of x. Which of the following is equivalent to f of 9? In other words, log base 3 of 9. Now it looks like what they want me to do is they want me to do the change of base formula. Okay, so very simply put, the change of base formula, if I have log base b of m, the change of base formula says that I can pick any value I want for the new log base. So log base k. Okay, and I'm going to make it into a fraction. Log base k over log base k. We're going to put m on top and b on the bottom. So what this would look like is this would be log base whatever number of 9 on top over log base whatever of 3 on the bottom. Now, that's definitely not going to be u. This has 3 on top, not going to be u. This has some weird 10 that shows up, and this has 9 on top and 3 on the bottom. Now, the k that they chose was 9. It doesn't matter what you choose, as long as it's the same number. So if I wanted to, yeah, I could say log base 9 of 9 over log base 9 of 3, and D is going to be a possible answer using the change of base formula. The function g is given by g of x equals log base 5 of x, and the function h is given by h of x equals log base 25 of x, which of the following describes the relationship between g and h. Now, probably the best way of doing this is maybe setting both of these up as its own special version of like whatchamacallit, the change of base formula, where I would take u, right, and just go with me here. It's just, I mean, there's other ways that you could do this, but maybe once I do this, you would look at this type of problem and be like, oh, okay, I get it. So I know how to do one like this from here on out. Again, just go with me here. If I were to use the change of base formula, but use instead of base 10 or ln base 5, I would say that g of x can also be written out as log base 5 of x over log base 5 of 5. And what that does is that gets me log base 5 of x over 1. No big deal. Which, common sense. Come on, what are we doing here? But again, go with me here, and maybe by doing it this way, it helps us understand what answers like this from here on out will be. H of x, if I continue with the log base 5 trend, would be log base 5 of x over log base 5 of 25. Now, log base 5 of 25 is log base 5 of 5 squared. Which means if I bring the 2 down, like this, that becomes log base 5 of x, bring the 2 out, 2 times log base 5 of 5 becomes 1. So you cross out. So we get log base 5 of x over 2, which is half of log base 5 of x. So while g of x was log base 5 of x, h of x is half of that. Huh? Right? So what we could say is h of x is half of g of x. So for equal input values, the output value of h is half the input value of g. So right away we can go with the answer of A. So yeah, definitely a strange type of problem, and it doesn't seem that way but 25 is bigger than 5. It seems a bit confusing, but that's what you would get after you plug stuff in. You actually get half the input value. So, weird, but that's how you do it. Simplify the expression ln of x plus 3 plus ln of y minus 3 minus 2 ln of z minus 1. Remember, ln is just a fancy type of log. Ln of x is the same thing as log base e of x, which means ln follows all of the same rules as log base e. So you would look at these guys first and notice that these ln's are being added to each other, so you multiply the insides. ln of x plus 3 times x minus y minus 3 is going to be x plus 3 y minus 3, bada bing. Now you still have minus 2 ln of z minus 1. What I could do is leave that as is and bring that 2 up there. So you have ln of x plus 3 y minus 3 minus ln of z minus 1 squared. When you subtract ln's, you divide the inside. So finally, our answer is going to be ln. You become an entire numerator, x plus 3 y minus 3 over z minus 1 squared. And that guy's going to be A. Expand the expression log base 2 of x cubed over yz to the 6th power. Now we're working backwards. Rather than moving things into a single logarithm, we're ripping things apart. So what you really want to do is rip them apart from the division part first. Whenever you're dividing inside a log, it's because you subtracted the logs in the first place. So step number 1 is to say, all right, well, log base 2 of whatever the numerator is minus log base 2 of whatever the denominator is. Now, what we could do is we could focus on exponents here and then something else here, but let's not kill two birds with one stone. Let's just take it one step at a time. We're going to leave this as log base 2 of x cubed for now, knowing that something's going to change later. All right. Whenever you're adding, or rather multiplying on the inside of logs, it's because you must have added in the first place. So me misspeaking there was kind of like me thinking ahead. All right. If I'm multiplying y to z squared to the 6th, inside the parentheses, it's because I added them in the first place. So log base 2 of y plus log base 2 of z to the 6th. So let's just quick distribute that negative real quick. And then we'll deal with exponents. Log base 2 of x cubed minus log base 2 of y minus log base 2 of z to the 6th. All I did was distribute the negative. Last step is any exponent living inside the parentheses, bring it out front. So finally we end up with 3 log base 2x minus, nothing happens here, log base 2y minus 6 log base 2z. And that's going to be a baby. Let f of x equals 3 to the x minus 1 and g of x equals 9 to the x plus 4. Find x such that f of x equals g of x. Well, that's just fancy talk for let's set these guys equal to each other. So 3 to the 3x minus 1 equals 9 to the x plus 4. Now, whenever you see a power equals a power, you really want to see if there's a way you can make the bases the same. And you can with this one. 3 you can't do much with. You're done. But 9, I can write that out as 3 squared. So I have 3 squared to the x plus 4. Again, on the left, not much you can do. But on the right, when you have a power taken to another exponent, you multiply exponents. And when you multiply 2 to x plus 4, that's distributive property. So 3 to the 2x plus 8. Now that we have a 3 to the stuff equals 3 to the stuff, we could set the stuffs equal to each other, leaving us with 3x minus 1 equals 2x plus 8. And now it's just a regular old Algebra 1 problem where you have variables on both sides of the equal sign. Minus 2x, 3x minus 2x is 1x, x minus 1 equals 8, add 1, x equals 9 is my guy, which means b is my baby. Solve the inequality log of x minus 8 plus log of 2 is less than log of 3x plus 4. Whenever you see logs a part of every single term, that's a good thing. But what we need to do is we need to combine the logs as often or as much as we can on each side individually and then take it from there. A log of stuff plus a log of stuff means I multiply the insides. So you're going to have log of 2 times x minus 8. I know when I wrote that kind of backwardsy, but I like viewing distributive property in that way. That's going to be less than log of 3x plus 4. So let's quick distribute here. Bang, bang. Log of 2x minus 16 is going to be less than log of 3x plus 4. Now, a gentle reminder, log is the same as log base 10. I have log of stuff is less than log of stuff. How do I get rid of the logs? You can cross them out. You can just cross them out. But why can you just cross them out? Because if I were to make these both exponents and take 10 to the stuff and 10 to the stuff on both sides, the 10s and the logs cancel each other out because that's log base 10. And what you're left with is 2x minus 16 is less than 3x plus 4. And now it's just solving inequalities that you would have seen in the ugly parts of Algebra 1. Right? Subtract 3x from both sides. That gets you negative 1x minus 16 is less than 4. Add 16, and that gets you negative x is less than positive 20. Divide both sides by negative 1 in order to get rid of the negative. And whenever you divide an inequality by a negative number, you flip the sign. X is greater than negative 20 here, which is going to be A. So the problem looks bad, but really wasn't. It was fine. I lived. I survived. Ms. Rodriguez wants to save for a new luxury yacht. Good for you, Miss Rodriguez. You and me both. I need more subscribers, though. She currently has 80 grand in an account that pays interest continuously and will need 500 grand in total. If she leaves her money in the account for 10 years and does not add anything, what interest rate would she need to achieve her goal? Okay, use the equation below where A of t is the total amount of money, P is the principal starting value, R is the interest rate, and T is the time in years. So what we need to search for is some magical interest rate that's going to turn 80 grand into $500,000 in 10 years. Whatever bank this is, I want it. I want it. I'll tell you one thing, it's not Diamond Credit Union, that's for sure. All right, what do we know? Well, this is what we start out with. So that's going to be my P. Okay, 80 grand. U are going to be what we're saving up for, so $500,000. 10 years. R is what we don't know. And E is the letter E. The number E, technically. So we have 500,000. Right? Equals 80,000. E to the R times 10. Divide both sides by 80,000. Divide both sides by 80,000. And I believe that gives you 6.25 equals E to the 10R. Now, up until this point, we didn't need to rely on this. But now we do. So what we're going to do is we're going to... not yet. Let's ln both sides, because I forgot about that step. Ln both sides, cross u out. That leaves me with ln of 6.25 equals, drop down the 10r. Divide both sides by 10, and now we could just throw all this into our calculator in one step. So r is going to equal whatever ln of 6.25 over 10 is. All right, so let's run to our calculator, use our calculator to figure that out. Come up with the best R that we can. All right, so just one thing that we have to do here is type in ln of 6.25. So where is it? There you is. ln of 6.25, and then taking whatever gross that number that is, gross, whatever number gross that is, and dividing it by 10. And we get 0.1832, which I'll round up to 0.1833. And then we'll go back to the main problem and just do it, like Nike. And we ended up with R equals 0.1833. Now, what does that mean in percentage terms? Well, whenever you want to turn a regular decimal into a percent, you just multiply by 100 or move to the right 2 times. So in this case, moving to the right 2 times gives us a wonderful interest rate of 18.33%, which is extremely irrational and unreasonable. But maybe there exists a bank out there in heaven. Thanks for watching. In a semi-log plot, which of the following pairs of functions appear linear as parallel lines? Well, when you're looking at semi-log plots, what's going to happen is anything that's exponential, anything that's in the form a times b to the x will appear as straight lines. Again, anything that's exponential that has the same base is going to appear as a straight line. So anything that's not exponential is not going to appear as a straight line. It's going to be distorted. That's what semi-log plots do. Instead of going up by regular numbers, they go up by 10, and then all of a sudden you become 100, and then all of a sudden you become 1,000. So what's happening is the exponential stuff appears linear. The exponential stuff appears linear. So a gives me two linear functions, 3x and 3x plus 5. On a regular coordinate plane, those are going to be parallel, but this is not a regular coordinate plane. This isn't going to be parallel in any sense of the world because these are cubics, and what this does is just make this 4 times taller. So you're no good. Okay? Now 5 to the x and 2 5 to the x are both exponential functions with the same base of 5. So it's going to be c. There's temptation to look at d and say, ln's, because there's semi-log plots, and a log plot is for ln. No, it's not going to be you. Okay, semi-log plots only do this for exponential functions, so C is going to be the answer that makes sense in this case. C and only C. Yes and only yes. Let f of x equals 2 log base 2 of 3x plus log base 2 of 2x minus log base 2 of 6x. All of those logs. It's like we're building a cabin. And then we have just one down here, but a bunch of stuff happening on the inside. So what am I supposed to do? Condense f of x into a single logarithm. So I'm going to need some space, so I'm going to write this over here. The first thing that I want to do is take these 2's, right, or just that 2. I was thinking maybe there would be more. Any coefficient that you see in a log, you're going to make an exponent. So step number 1 is going to turn that first term into log base 2 of 3x squared. We're not going to touch this guy yet. We're not going to touch this guy yet. And even in the next step, we're not going to touch either of them either. Because when I square a parentheses, I square both parts of that parentheses, not just like the x. So this actually becomes log base 2 of 3 squared, which is 9, x squared, plus log base 2 of 2x minus log base 2 of 6x. Whenever you add two logs of the same base, you multiply the insides. So this guy becomes log base 2 of 18, because 9 times 2, x squared times x is x cubed, and then I still have minus log base 2 of 6x lingering around. When you subtract logs of the same base, you divide the insides. So you become log base 2 of 18x cubed over 6x. And that's going to simplify to 18 over 6 is 3, x cubed over x is x squared. So f of x, written as a single logarithm, is going to be log base 2 of 3x squared. Fun stuff. Now for part B, I'm going to do literally the opposite. I'm going to take something that's already put together and rip it apart. So let's take u, move it down here, right, and say log base 2 of 64x. Well, if I'm going to rip stuff apart, I'm probably going to do the opposite of me turning that coefficient into an exponent and me taking an exponent and turning into a coefficient. 64 is 2 to the 6th power. Okay, and then I have x just kind of lingering there. All right, so what I'm going to do first is to separate these. I'm going to realize, well, if I'm multiplying 2 to the 6th and x, it's probably because I added previously. So you become log base 2 of 2 to the 6th plus log base 2 of x. Take that 6, bring it out, and now we end up with 6 log base 2 of 2. I know you're going to want to turn that into something, but don't. Plus log base 2 of x. So g of x, when ripped apart, is 6 log base 2 of 2 plus log base 2 of x. Now, what I want to do is find an x such that f of x equals g of x. Well, I want them all put together in order for me to do this. I want to use this version of part A, the one that's already condensed, and this version of part B. Because by setting these two equal to each other, I have a log base 2 of 3x squared equal to a log base 2 of, what was it, 64x. Okay. When you have a log base 2 equals log base 2, or a log of anything, as long as the same base equals a log of anything, you cancel each other out just like that. Here's why. If I were to take 2 and make that a base and make my logs an exponent, that cancels you out, leaving me with just 3x squared equals 64x. Now what I want to do is I want to subtract both sides by 64. So let's go and do just that. Let's go up here and show those steps. We've got 3x squared minus 64x equals 0. I can whip out an x, but that's it. 3x minus 64. Now, my zero product property says you're going to be 0. Here, if I'm going to do this, I have to do 3x minus 64 equals 0. To save some time, I'm going to add 64 to both sides. So that's going to equal 64. And I'm going to divide it by 3, and so x is going to equal 64 over 3. Now, here's where you have to be very, 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 very careful. Whenever you're solving a log and you get more than one answer, chances are one of those answers won't work. And why won't it work? Because it's going to have the log of a 0 or a log of a negative, both of which are illegal. You can't take the log of a 0 and you can't take the log of a negative number. This guy right here is not a possibility. Because if I were to take you and plug you into literally any one of these, you won't work, you won't work, you won't work, you won't work. However, if I take 64 over 3, which is 21.3 repeating, I could plug that into 3 and it would stay positive. Plug it in here and it will stay positive. Plug it in here, plug it in here. It will all work for all of them. It'll work for all of them. So you are a solution, whereas that 0 was not. So keep in mind, you're going to have answers that don't work. But that, boys and girls, concludes free response question number 3. One more to go and we're done this Unit 2 practice test. Let's go to the beach. Nicki Minaj. We're at the last free response question. The amount of bacteria in thousands found on the beach has been steadily declining. Well, thank goodness for that. Scientists want to create a regression model to show the number of bacteria as a function of years. So 1, 2, 3, some bacteria in thousands, whatever that means. Lots of bacteria, less bacteria, good. What's a logarithmic regression equation that could model this situation? Well, that's going to appear as ln reg in our TI-84 plus. So what we're going to do is we're going to go off to the side. Okay, we're going to type all this information. We're going to stat edit, type in all that information, and then we're going to get ourselves an equation and use that equation to help us answer for B and C, because B and C are going to ask us how many years, blah, 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 how much bacteria, blah, blah, blah. And so we're going to do not only coming up with our equation, but we're going to do some reg-EQ stuff. So storing the reg-EQ. If you know what I mean, you know what I mean. If you don't, just watch the video. Let's do part A. You'll see what I mean. All right, let's get gross and talk about bacteria. We'll go to stat, edit. We're doing a logarithmic regression equation, which is ln reg. So this is the direction that we go in. Type in your numbers like so. Go over here, your bacteria in thousands. We have to keep that in mind. 9.9, 7.8, 6.7. Don't make a typo. So far, I think I'm good. 5.8. All right, now B and C looks like we're going to need to use this equation later. So not only am I going to come up with an equation, I'm going to store that equation in my calculator. So yeah, we're going to go to stat. Yeah, we're going to go to calc. Okay, ln reg is right there at 9, so we can click 9. That is your logarithmic equation, and ln reg pops up. Again, we need to store this, so we're going to go to store reg-EQ, vars, go right to y vars, enter, enter, and now that's going to store it in y equals once I hit calculate. And I need to hit calculate so I can answer A. And A is going to be gross. 9.885 plus, well, minus 2.939 ln of x. So let's go off there and write that out. So for part A, I ended up with y equals 9.885 minus 2.939 ln of x. Gorgeous. How many years until there are 2,000 bacteria? Well, 2,000 bacteria will show up as 2. So at some point we're going to hit 2, and I'm going to run to my calculator, go to the y equals thing, plug in 2, and find out where my ln equation and this 2 will intersect, and that'll give me the answer that I need. Alright, so now that we have that equation, part 2 is asking me how many years until there are 2,000 bacteria in a sample on the beach. So we want to find when this equals 2,000 bacteria. Now, that means we use 2. So I'm going to go to y equals and use 2 and plug that in. And hopefully we see everything. Maybe we do, maybe we don't. My eyes are bad. So I'm going to go to window and I'm going to extend my x value to 20. And that should be more than enough to see the intersection take place. So hit graph. There you go. Now what I want to do is I want to find out where those guys intersect. So second calc 5 will let me do that. So let's scroll a little bit closer. Enter. Go to the right a bunch of times. Oh, did I not hit enter? I guess I did. Let's try it again. Enter. Now let's do the second one. Go to the right a little bit. Good. Enter. Enter. And we're looking at 14.627 years. 14.627 years. So let's go over and write that out. 14.627 years. Okay. How many bacteria can be found in a sample after 6 years? This actually is a lot friendlier. All we have to do is just go to the table. So let's go to the table and see what happens. Part C is asking us how many bacteria can be found in a sample after 6 years. So this is pretty friendly. So we're just going to go to second table. We could see 6 already. Oh, I still have my old guy there. Don't worry about it. We're looking at y sub 1 because that's where our equation lived. Y sub 2 is just us plugging in for 2,000. So don't worry about that. But we get 4.619, which means 4,619. So let's go back and write that out. Now, the number that we got was 4.619, but what that means in this case is 4,619 whatever. Bacterium. All right, so that concludes our Unit 2 practice test. So I hope this is helpful. I hope you enjoyed it. I hope you study your little keisters off and get good grades. And if you do, come back and tell me how great you did, because I care about each and every one of you. All of my subscribers, all 1 million of you. I'm projecting this into the future. All right, guys, thanks for watching. Love you. Bye.